Welcome back, physicists. Today we are going to be looking at 9.2.2, and I know that you had a few problems over the weekend. You are in luck if you did not quite finish those. You're going to have a little bit of time today, I think, but definitely time before tomorrow, because what I'll do is I'll take the 9.2 worksheet with those four or five problems, tomorrow at the start of class before we go out to bridges. So, quick little review. We have been talking about momentum this chapter. And last class we looked at two particle collisions, where we see that if there's two objects traveling toward one another, before a collision they have some mass, some velocity. They collide, they exert forces on each other via Newton's third law, and then they repel or move away from one another in this example. And what we determined was that the same momentum was present at the beginning as it was at the end, which led us to this idea of the law of conservation of momentum, which is what you focused on with your assignment. Now, just as a reminder, because I don't have it written right here, conservation simply tells us the following. PI, or P, and let's say we have A and I, PAI, plus rho, and I guess rho rather, initial momentum of A plus the initial momentum of B, turns out is exactly equal to the final momentum of A plus the initial or the final momentum of B. And just to kind of make sure that this is really clear, we also can write it, and I use a fancy L. This is the linear version. If you take the initial momentum, turns out in an angular sense also, it is equal to the final momentum in the angular sense, where these things, just like we saw here, this could be mass times velocity, where these angulars are moments times omega, or angular velocity. Okay, so there's a quick review. Today we are going to expand on that just a little bit, and in 9.2.2, our focus today is going to be on recoil. So we're just continuing right on, and here we go. We're going to talk about recoil. Okay. When I think about recoil, I think about firearms, just for complete honesty. When we look at a situation, let's say we have the following, and this is going to be a lazy drawing. But let's say we have a boy standing on a skateboard, and we're going to make him fairly large, at least in comparison. So here he is, he's standing on a skateboard, and his head just barely fits here. Okay, I'm going to say that there's a ball behind him. Like if we're looking like this, here's the floor that we're looking at just so we can see and track a little bit of motion. So there's a ball on the floor beside him. Now, there's another person on a different skateboard working without friction, where let's say this is a smaller child. So some kids learning how to skate. Okay, this is the before situation. Now, I'll just go ahead and write this, before. And then I'm going to say, look, this picture changes in just a little bit, but we are going to let person A, and I'll label person A and B. Let's say hypothetically that this bigger person A pushes B. Okay, now right off the bat, as we're looking at this, we're going to make sense of our system as being these two people, the big person A, little person B. And A pushes B. Now, it might seem like this force that's applied isn't within the system, but notice, everything that's here in the system is everything that's there, and the force is being generated within the system. So, why I'm mentioning that is we recognize, and if not, hopefully you'll believe it, the internal force is what's being applied here, which means it's already within the system. So this implies that conservation is at work. Okay, because my force is being generated within the system that we're looking at, momentum and its conservation applies. So if we have this person A is going to push person B to the right, and I just want to think about what happens. So here I'm going to redraw this picture, and it's not going to be perfect, but we're going to notice something. Unless person A is like way, way, way heavy, like in a ridiculous amount of heavy, then what we should see is that this ball that we were referencing, that person A was right up next to, is going to be a little bit further away. Not a ton, but a little bit further away. So the reason that this happens is that when this person shoves that child, they're going to be pushed back, at least a little bit. And I will say, check it out, here's the velocity of A. Now, if you think about this situation, pick somebody big in the class and somebody small, and think about what happens if they're both on skateboards and the big person pushes. The big person is pushed back a little bit, but the smaller person with much less mass is going to wind up being pushed significantly further, and not only are they going to be pushed further, but when they move away, their velocity is going to be larger as well. Now, what we're seeing is that equal but opposite reaction applying with the law of conservation. So what I see, and what I really hope you notice, and without being in class to talk about this, it can be a little bit more challenging, is A has moved a little bit back, moves back a little after this push, and then simultaneously, this person B moves forward a lot. Now, a lot is subjective, right? So I'm talking, when I say a lot, I just mean compared to person A. Cool. Now, if we dig into the conservation of momentum here, we're going to see some pretty handy stuff. Now, want to stress, if needed, please elect somebody right this second to get up and pause this as we go through, because if there's any weird little pieces that we need to make sense of, then we might have to pause it and talk as a class in my absence. So let's just start off. We have two people, A and B, and they're not moving. So I will make that last little note right here, velocity, and I think it was this blue color. Velocity equals 0. Okay, so if we apply conservation of momentum, let's just see what shakes out. We have the initial momentum of person A plus the initial momentum of person B, and we claim that this should be, not claim, it has to be, because of the law of conservation, the final momentum of person A plus the final momentum of person B. So because these forces are applied internally within our system, we don't have to do anything else. We have conservation. Cool. Now, in the beginning, because their velocities were 0, and I'll make that little note here, what we get is that all of a sudden, their initial velocity was 0. Or sorry, their initial momentum. So initial velocity equals 0 implies that the momentum ought to also be 0. So let's check out what happens here. On this other side, what we wind up getting is just our final of A plus the final of B. So nothing crazy has happened yet. Now, it doesn't matter which way we decide is positive, but it's pretty natural to think that B winds up looking like the positive one to me. So what I'm going to do is I'm going to keep B on the positive side, and I'm going to subtract the final momentum of A. And in doing so, if I subtract the final momentum of A from each side, here's what I wind up with. So I see that B's final momentum, the little smaller person moving forward, is equal but opposite to the larger person's momentum that's moving the opposite direction. Okay, a little bit of substitution is all that we need here. If we just plug in what it means for momentum, I know that that is the mass, and I'm going to keep that negative. It's the mass of person A times the final velocity of person A. And it turns out that that is exactly equal to the mass of person B times the final velocity of person B. I'm sorry. Okay. Now, it's this point that I would kind of make sure, we're going to go a step further, but this is access for future problems. Maybe, just maybe, future problems can start here if we have this situation with VI equal to 0, or if you'd rather, we can just say rho I equal to 0. We can just jump in here. And what I mean by that is in any other situation where we have this, we already have a formula where depending on what I'm trying to solve for, I can. And we're going to see this applied like in just a moment. Okay, so hypothetically, and this is purely arbitrary, meaning like whichever one we go with is fine, but if I wanted to consider how fast person B, that smaller person, is traveling after the push, I can solve this. So I'm going to switch sides, and I know that it can be weird, but I'm going to solve for this, and I want it on the left side. So let's see, I would have negative mass of A, velocity final of A, and then I just, divide by the mass of B. And it turns out that here we have a nice expression that if we have initial momentum of 0, and we know how fast they're traveling at the end and their masses, then we can find how fast somebody must be going in the end. Cool. All right. Now, one more little step in this one is I'm going to put another star on it. What we can do, and what I want you to really recognize, is that if I rearrange this just a little bit, and I were to write this as the masses next to one another, mass of A, negative mass of A because the numerator, divided by the mass of B, times the final velocity of A, then what we notice is that the velocities of B and A, they vary. Now, they vary with regard to whatever this constant is. So if these masses were numbers, this is just some number, right? It could be a decimal, it might be a whole number. However, the important part that I want to highlight here, and I'm going to stick this one in red, their velocity, and I guess velocities, because it's both of them, vary with, so they just change, right? The velocities change depending on the ratio of masses. Ratio of mass. Okay. So if person B happened to be larger, then we're going to see something different occur when A pushes on them. And we're going to deal with this situation. We're not going to see all of them. But we have an easy way to calculate out final velocity if you give me some masses. Now, this idea of recoil, which that's what's going on here. We have recoil, and we look at the situation where somebody's standing and they push on a frictionless surface. The exact same thing happens with firearms. So in movies, when you see somebody shoot a firearm and they're launched backward, that doesn't really happen. Or when somebody shoots a firearm and something else is launched way forward, unless that is a ridiculously like sci-fi type weapon, that's not going to occur because momentum is conserved. Okay, so today's going to be pretty chill. We are going to see one really cool application of this. It's nice to see that, hey, we can push people, or maybe, just maybe, we would see this like on a skating rink if we have ice and there's people pushing each other. Pretty common situation. A much cooler situation in which we can apply this, and I'm going to sneak this in as an example, and then we're going to work through this example. I'm going to give you guys some time to work on some problems and a little bit of time, hopefully, to finish anything that you hadn't over the weekend. So, for this example, we're just going to call this space propulsion. And the idea of how does one move in space is a weird one, because like we can move on the ground by driving because our wheels interact with the ground and it's friction, but in space there's not even any air because it's a vacuum for us to push off of. So we have to be able to move somehow, and we're going to see conservation momentum explain this. So here we go. I'm going to use a little editing magic. If somebody would stand up and pause this once I get this problem shown, that would be great. And here we are. So I'll have you guys jot this down in your notes, and I'm going to talk about it for just a second. I imagine you guys are writing. We have an 84 kilogram astronaut that shoots a 35 gram, and I'm going to underscore that because the fact that that is in a different unit causes me stress. So we have this astronaut that shoots a 35 gram burst of hot gas from a spacesuit, so must be some boosters on the back, and it's fired out of the spacesuit at 875 meters per second. Okay, they are both at rest, the astronaut and the weapon, or the astronaut and the jetpack, and we're looking for the velocity after shooting. So, if you guys will, whoever wants to come up and pause it now, I'll give you a little bit of time, but I'm going to start modeling this and working through this in 5, 4, 3, 2, and 1. All right, so like every other time that we ever do these problems, I'm going to start with the knowns, and let's just kind of dig in. So if we want a picture, we can. Here's an astronaut, and I'm just going to draw a point, Here's astronaut, and they're initially at rest. So VI equals 0. Okay, and then something happens, and this is the shoot or the shot of the booster, and we wind up having two different things. So we have an astronaut, we see the booster, the gas, goes this way, gas, and this is the velocity of the gas, I suppose, and then because conservation momentum occurs, we must see that simultaneously the astronaut goes this way. So here we are. We have a little picture to make sense of it. We're floating in space, shoots out the gas, apparently to the front of them, and they are repelled or recoiled backward. All right, so there's our situation. So from here, we should be able to just knock stuff out and see if we can't find this astronaut's final speed. So here we go. I'm going to use A for the astronaut. The mass of the astronaut I know is 84 kilograms. And the mass of the burst, which I'll call B, we know is 35 grams. So grams is my base unit. To get to kilo, it's 3 to the left. So if I go to 35 grams, that's 0.035 kilograms. And I've done the conversion here using that King Henry died by drinking chocolate milk expression. Okay, a few other things, and I'm trying to make it so I can see everything here. I know that the initial velocity of A is 0, because she's not moving. And on her jetpack, if she's 0, then this must also be 0. And only one more little piece of known. After the burst, that gas is traveling away from her at 875 meters per second. Now, I've decided to make the gas fire in the positive direction, which means we should be expecting the astronaut to be moving opposite, so negative direction, but we'll see how it shakes out. This is everything that I know. Okay. Beyond that, we're trying to find here the final velocity of our astronaut, and we're going to see if conservation can't hook this up. Now, I made the comment on the previous problem that there might be something that we can use, and I just want to kind of show this. If we wanted to jump in using conservation, we certainly can. The initial velocity of A plus the initial velocity of B is equal to the final velocity of A plus the final velocity, or sorry, final momentum of A plus the final momentum of B. My mistake. Now, something very similar to what happened on the recoil problem is going to happen here again. They're initially not moving. So regardless of their masses, if we multiply it by a velocity of 0, we're going to get 0 on the left side. This is 0 because they're not moving. And here we are, rho AF plus rho BF. And then we are trying to solve for velocity of the astronaut final. So I'm going to keep it here, and I'll just say, all right, well, negative rho BF, my final velocity of that boost of hot gas, is exactly equal to the momentum of my astronaut. And I keep interchanging those language, and I'm so sorry. The opposite of momentum of my blast or my boost is equal to the final momentum of the astronaut. All right, now, just looking above, because we saw something super similar. This is what I've just done, which means this is going to be my next step, and this is going to be my next step. And all I realize is that if I'm looking for the velocity of B, I can use MA/VA, or if I want to switch this around, I could have solved for VA, and it would be MB/VB. And notice that they match. Mass of A, velocity of A would be in the numerator. So if I'm looking at this, if I want to find the final velocity of A, I know that if I want to expand, it's the mass of A times the final velocity of A. And this is negative the mass of the boost times the final velocity of the boost. So notice, mass of B, velocity of B. I switched around because this is mass of A, velocity of A, but it's the same idea. We're just switching the letters. Okay, one more little step. I'm going to move the velocity of A final to the left side here. And let's see, it would be negative mass of B over, and I'll write it out like this, I suppose, velocity of B final divided by the mass of A. And it turns out that we have like all of this information. So let's see, I have negative, mass of B was 0.035 kilograms. The final velocity of B, we were told, is 875 meters per second. And we are dividing this lovely value by the mass of A, which we were told is 84 kilograms. So I don't normally include my units in, but this time it works out and I happen to do it, and it's really nice because we see that the only unit left is meters per second. We are solving velocity, so that makes sense. So let's just check here. Grabbing a calculator, we have negative 0.035 times 875 divided by 84. And I want you guys to confirm this, but I wind up with negative approximately 0.36 meters per second. Now, this is pretty slow. It takes 3 seconds for this person to move a meter, but consider what just happened. They had 35 grams shot out of their gun. This is rocket propulsion, and it explains why, even in space when there's nothing to push against for our rocket, we can still get moving. And it's not that we're pushing against anything external, but the hot gas applies a force to the engine in one direction, and the engine must apply the force to the hot gas in the other direction, and momentum is conserved. So, our final lovely statement, the astronaut travels in the opposite direction. That's what that negative is telling us. Direction of the gas at a cool and collected, and I'm not going to use a negative here because that's what the opposite means, 0.36 meters per second. So if they are, and this is just a fun hypothetical, if an astronaut's doing an untethered spacewalk, so there's nothing to tie them on, and they got 10 meters away, and they fire their weapon, there's nothing that's going to slow them down, but it's going to take, let's see, 3 seconds to go a meter, so 30 seconds they're going to have to drift and hope that they hit the space station or spaceship, because if not, they are going to have a bad time. All right, so this lesson was a single example. We should have roughly 20-25 minutes left in class. So tomorrow I will be taking 2 assignments. I will be taking the worksheet that I gave you guys last class, and I also want you to spend a little time on homework 9.2.2, which you will find waiting for you on page 249. And I want you guys to do problems 23 through 25. And because I am on it today, I will go ahead and put them right here. If you want to send somebody up to pause the video before I end it, that would be perfect. But here are the 3 problems. Don't trust the challenge, as always. Maybe it's a challenge, maybe it's not. You won't know until you really try it. Don't believe them. All right. Well, hopefully you guys found this video helpful. We will go over the 9.2 questions thus far tomorrow at the start of class. And please use the remainder of time to get finished on these 3 problems and any problems that you didn't finish over the weekend. All right. Later, Raiders.